So today we're going to talk about the different bus systems and bus frameworks that are used on transport aircraft. So we're going to start with, we're actually going to kind of work backwards in terms of when these were. So most modern aircraft, pretty much any modern aircraft that runs on AC power, 120 volts, 400 hertz, is going to use a split bus system. And the idea behind a split bus system is that under normal operation, when the aircraft is operating correctly, the two or more main buses are split from each other. So the primary power source on most transport aircraft are going to be the main engine generators, the engine-driven generators. Power sources are broken up into primary, secondary, emergency, and ground. And some power sources are more than one. But the primary source is always the engines. The aircraft wants to run on the engine generators, which are at all possible. The reasons for that is typically the engine generators are the largest or collectively have the highest load capacity. And so the other part of that is your secondary or emergency your secondaries tend to be run off an APU. If we have multiple engines running that can supply electricity along with things like bleed air and run hydraulics and other stuff like that, it doesn't make sense to have to run the APU constantly. It puts wear and tear on the APU, it burns additional fuel. And so our primary source tends to be the engine-driven generators, and this is what the aircraft is going to want to run on majority of the time. And so you can see this in this schematic, for instance. We have our two engine-driven generators at the top. I'm going to try to open my annotations pane and see what happens here. We have two engine-driven generators at the top, and they show a constant speed drive connected to the generator, and we'll talk about that, and a generator control unit. So those three items create or set up what the electricity is going to be coming out of the engines that the engines are going to produce with the generators that are driven by the engine gearbox. And that's not a very visible color. Let's try that again. So this let's move stuff rather than delete. Let's go back to 10. Okay, so right here, this area is on the engine. Maybe the GCU might be remote, but for the most part, the CSD, the generator are on the engine, and they're going to create power. And you can see there's one on the left engine in this case, one on the right. If you have 3 or 4 engines, you're going to have this assembly on each one of those engines as well. And going through different contactors, switches, and that kind of thing, power is going to be fed to the two, in this case, main buses. So typically what are called AC bus 1, AC bus 2, or you'll hear the terms, and if you have 3 or 4 engines, they'll have an AC bus 3 and an AC bus 4. But the other way you'll hear these is a lot of times AC bus 1 is also known as the left-hand main bus. AC bus 2 is often known as the right-hand main bus. Okay. These will power additional buses that are used for load shedding, and later on we'll discuss that as well, because many of these big aircraft, if we do have to go to a secondary power source like an APU, or if we have to go to a backup or an emergency power source, we're not going to be able to power everything on the aircraft. And so these are designed to automatically switch off and change over the different loads on the electrical system to compensate for that. So you can see from AC bus 1, in this case, there's like a utility bus, which is often things like lights and coffee makers and that kind of thing. There's an essential bus, which is going to be the items that absolutely must be powered for flight. So if we get into a true emergency situation, we actually will drop the AC bus 1, AC bus 2, and only pretty much power this essential bus. And then again, some more utility buses, service buses, that kind of thing. Those are all kind of secondary. So the majority of your loads are going to run off AC bus 1, AC bus 2, but you're going to have some really important stuff on an essential bus. you'll have your least important stuff on your utility and service buses. And those are pretty common terms industry-wide. So if we were in a situation where we lose a generator, we go down to a single primary, these systems are often designed where a single primary source is large enough to operate everything, still operate everything or the majority of items on the aircraft. So you can see here, we've switched now to a situation where we're only powering the aircraft on a single engine, but it is a single engine that is running. It's running a single generator. And my pen tool doesn't want it. There we go. And now this, instead of the power from each of these going to their buses, this switch right here, when this generator package, when the right generator shut off, this switch moved into this down position right here. And the switch below here moves, it's no longer in that position, it moves into this position here. And so now power for the bus 2 and the utility buses is coming from this, what's called cross tie, over and then powering the right hand half of, or the number 2 half of the electrical system over here. But again, you can see in this case, it's still coming from the number 1 generator. It's still a primary source. Now, it doesn't mean we can't turn on the APU. In fact, if you were in a case where you lost one engine, the crew normally would switch on the APU in order to have a second generator running, a second hydraulic source, a second bleed air source. So if they did lose the left engine, you've already got the APU running. But this is swapped over at this point. Okay. The next part is our secondary source, and this is the APU. And this can be a case where the most common use of this is on the ground, where we don't have engines running, say the airplane's at a gate, but there aren't ground or power or air sources available, or as the plane's getting ready to start its engines and whatnot. The APU is often used as a power source, but this is the secondary power source. So you can see now these contactors have switched to this APU tie. You know, both of these switches right here and right here have moved to this down position. It's disconnected from the generators. And now we are running both buses off of the APU generator. And one item of note I do want to mention is that, you know, right now everything is sharing a common voltage, common frequency. It's all whatever the APU generator is putting out. That's also the case when we have a single generator. Right here, everything is sharing a common frequency, common voltage. One thing we do have when we're on our primary sources like this, your left generator, your number 1 system, is going to be running at a certain voltage and frequency, typically right around 120 volts, 400 hertz. The right engine is going to be the same, around as 120 volts, 400 hertz, but the frequencies may not be in phase. So what that means is when they're in phase, it would be, you know, an AC is a sine wave. It's going up and down. And when 2 generators are in phase, it means their sine waves are coming up together and down together and up together and down together. When these are separate, because they're not tied together, you may have them out of phase with one another. And it's not a big deal because your items are powered by one or the other. Here, and when you have the APU, you only have a single phase coming in. This is also a similar organization to what will happen when we run on ground power. And I don't have a separate picture of it, but you can see there's an external AC cart here. So on the ground, if we don't want to use an APU, another secondary source on the ground is we can plug in external power, and this switch would move down here rather than the APU. And so it can go that route instead. And so that's another option. You can see there's this possible route here that's called a service route. That's used on the ground if you have a situation where all you want to power is things like lights and maybe a few things and maybe a vacuum cleaner outlet or something like that. So those would run off the service bus. It gives some cabin lights, power for like a vacuum cleaner, that kind of thing. And that's used if you don't have a flight crew or maintenance on board the aircraft, but you have people like aircraft cleaners or other stuff like that, or even flight attendants prepping the cabin. It's so that the rest of the stuff that runs off everything else would be separate. But for the most part, the APU, running this way is going to run everything, and everything's going to be on the same phase, the same voltage, the same frequency. The last source we have here is what's called an emergency source, and so this is only used if we're in a situation. Now, I'm not saying the APU can be used in an emergency. As you saw, we can run if we lose both engines, but the flight crew is able to start the APU. The plane is a glider at that point, and these planes will glide. But the APU can provide electrical power, which can run things like hydraulics. It can run bleed air. They can attempt to restart engines using bleed air, and they can run most of their instruments, actually all their instruments and everything like that. A true emergency source is now you've lost, not only are the engines not operating, but you can't run the APU as well. And these are both, don't get me wrong, if all you have in the air is an APU, you're in a pretty dire emergency. However, if you lose the APU as well, your emergency situation gets even worse. And so that's where we go to in this aircraft. This aircraft uses what's called a ram air turbine and an air-driven generator. This is a little propeller that essentially pops out of the side of the airplane. And as the airplane's flying forward, the air going over this turbine propeller spins it, and it turns a generator. And you can see here it powers what's called an ADG bus, which is there's just a few things that run off of it, as well as this essential bus right here. And some options that you might have, some things that it might be powering is it may power, typically an aircraft's going to have multiple hydraulic systems with multiple pumps per system. It might power one pump on one system that allows you to move your primary flight controls and drop the landing gear. It's probably going to power a very basic set of instruments or a single backup instrument. It's going to power a backup radio or an emergency comm, and it's going to power those kinds of things. And it is just barely enough. The idea is it's just barely enough for the aircraft to get on the ground. Other options are 727 that we have, for instance, instead of using a ram air turbine, it uses a battery. And so a battery being DC, it's connected to an inverter. Inverters take DC and make AC power. And so on the 727, it uses a backup battery that powers an inverter, which again powers a very limited set of AC equipment to allow you to fly the airplane or glide the airplane to the ground, hopefully safely. All right, Mike's dropping off some stuff outside, looking at me through the window. Okay, another option then. So that was a split bus system. The other type of bus system, major bus system, you'll see is a parallel bus, and this is what the 727 has that we've gotten familiar with. And this diagram should look kind of familiar because it is very similar to the schematic in the aircraft, the switches that you have all been using to control to power up the 727 in lab. So it's called a parallel bus because you have multiple buses in this case. And parallel comes from the term is that these buses where the split bus system, when all the primary sources, when all the engine generators are running, they're going to have, the voltage is going to be 120 volts, the frequency is going to be 400 hertz, but the the frequencies, the power is not going to be necessarily in phase with one another. A parallel bus comes from the fact that the phases are parallel to each other, or the phases, the phase of the 2 or 3 generators are all going to be together, synced with one another. And that's where the term, you can see there's a sync bus here. And so what happens is, let's kind of look at some things that we got going on. Normal circumstances, sorry, we'll start with this one, we're going to work the other direction. So starting with ground power, this is what we're doing in the lab. This is how we're primarily running the 727 in lab right now. And so the, what we're doing is we're bringing in, let me get my pen. There we go. Here's that external power receptacle. We're plugging in our plug over here. And then remember, you have to turn on the external power switch. And the external power switch is this contactor right here. So that connects the external power plug to the sync bus. And then we need to drop the sync bus down to each of our main AC buses. And so that's those 3 switches you turn on, typically left to right, 1, 2, 3. Those are these bus tie breakers right here. You're turning on 1, you're turning on 2, and you're turning on 3. And as you turn those on, power is able to flow from the external power receptacle into the sync bus. We turn on the first one, it comes down to AC bus 1. We turn on the second one, and it's able to come down to AC bus 2, and we turn on that third switch, and it comes down to AC bus 3. And then AC bus 3 also powers an essential bus. And you can see our essential bus here is AC. You can see there's a line going up and disappearing. When we talk about the DC system, this is where that emergency power ties in on this airplane. It would come in from the top right here. And a battery with an inverter will power the essential bus. It could just as well be, if the engineers had decided, it could just as well be an air turbine or a ram air turbine, a RAT, or an air-driven generator, ADG. So when we go to use the actual aircraft, when we want to run the aircraft, if we have engine generators, typically what's going to happen is the APU is going to be started first. Again, the APU is a secondary power source. APU has a contactor that connects it to the sync bus, just like the external power does. So now we're running the APU and powering the sync bus, but you can see we have these bus tie breakers are not connected. But as we start each engine, we start generator 1, we connect generator 1 to AC bus 1. Okay. And this is open. Okay. And once we've started all 3 generators here, we can shut off our APU generator. And so once we shut the APU generator off, and now we can close our bus tie breaker, and there shouldn't be this line here. This line's not here anymore. Get rid of that. Okay. We close that first bus tie breaker, and now generator 1 is going to power our AC bus, and it's powering our sync bus. Okay. But what we have to do is, before we can hook our next generator up to the sync bus, we have to do what's called parallel the generators. And there's a couple little knobs in the aircraft, and you adjust those knobs, and it moves, it changes the phase of the frequencies, and we got to get them lined up. So we compare the sync bus frequency up here. There's a selector. We select which generator we want to compare the sync bus to. So we select generator 2 in this case, and there's 2 lights that'll blink, and they blink based on the phase. And as we turn a little knob, those lights start to blink closer together, and then finally they shut off and they extinguish. And that tells us that we've now got generator 1 and generator 2 using the sync bus in phase with one another. And at that point, then we close the second bus tie breaker. And now what happens is when you have two generators that are connected together, they're close to being in phase, and you connect them together as they electrically through electromagnetism, the forces, the electromotive force that's produced in the wires and in the windings in the generator, they actually lock in with one another. And so now they will spin, even if there's a slight difference in how fast they're spinning. That magnetic force will actually pull them in until they're in phase. So they'll spin at the same speed. They'll lock in voltages. They'll lock in frequencies, and the frequencies will be now in phase with each other instead of out of phase with one another. And then the same process is done for the third generator. So again, we're going to turn that switch to Gen 3. We're comparing the sync bus frequency. We compare the sync bus frequency here to the generator 3 frequency down here. We adjust the frequency control knob to either speed up or slow down the AC bus 3 frequency until it matches the sync bus. They're called sync lights, syncing lights go out. And that point then we can close the third bus tie breaker. And now all three generators are powering their buses, but they're also powering the sync bus. And this is this is the normal configuration that the airplane would be in flight on its primary sources. Now what happens is if we lose a generator, say generator 2 goes out, now you can see we've lost the power coming up from the bottom. We've lost this power coming from generator 2. And now we have power coming down from the sync bus. And this bus 2 won't even necessarily, the items on it won't even see a change. They'll still be in phase. Now, it has its advantage in that way, is that we don't have to wait for contactors. With a split bus system, there is a slight delay, a slight trip where you'll see stuff kind of as those contactors switch over. But the big disadvantage with a parallel bus system is that they are connected all the time. And so when this generator 2 went out, if it failed for some reason and it sent out a surge or something catastrophic, it could have the potential to send that surge or whatever it might be to the entire electrical system of the aircraft, to all three main buses. Whereas a split bus system, by having two buses that are normally isolated, if you have a major failure on one bus, and it could be beyond just the generator, if an item connected to bus 2 or bus 3 or bus 1 went out in a parallel system, it could also cause problems on the other buses. Whereas if you have a split bus system, like the first example I showed, and something goes wrong on bus 2, that the fact that they're isolated and those contactors in the more modern aircraft, there are computers monitoring all this stuff, they would see that problem before they switched over the transfer switches. And so you don't have as big of a risk of a failure on one bus taking out equipment on every other bus. This can go a step further here. We could lose a second generator, and you can see we're still powering buses 2 and 3 from our sync bus. Normally, again, the generators are sized so they can drive all, if not the majority, of the electrical loads. You might have some load shedding built in. We'll talk about that, but this one really doesn't have much in the way of that. The load shedding on the 727 has to be done manually. That is turning off certain loads. If there is a generator failure, the crew would have to pull out checklists, and it would say, okay, turn off this, this, and this, so that you don't. Maybe you turn off the coffee makers. Maybe you turn off some of the lighting. And that kind of thing, in order to reduce the loads on the systems and go from there. The last way, APU running. So we go back. So paralleling with an APU, it can work the same way. But now, you can have the APU running each one, and then you can tie your generators to it. And so this is, again, the APU can run all three. This is the way, if we have a working APU, this is how you would power the aircraft on the ground when you're doing that. So with each of these different setups, we want to look at how they're controlled and how indications work. So here's an example. Here's going back to that first one, that split bus system that we discussed. And on the split bus system on the right, you can see the control panel on the left. And this is the CRJ200. It's similar. The reason I use this is because it matches our simulator. So if you remember from the time you were in the simulator, you used this electrical power services panel here during your time in the simulator. So this is the electrical power services. This is the overhead panel that controls the electrical systems on this aircraft. Now, a lot of this stuff can be done automatically. A lot of these ties and contactors and things like that are normally managed automatically, but there are a few that can be activated manually, or can be activated manually if the automatic systems fail. So kind of comparing what's what, if we look at the switches, these are set up in a similar fashion or similar format to what's on the aircraft. So here's your Gen 1 and Gen 2 switches, and you can see these turn on. By turning these on, what you do is you energize the magnetic field. The magnets in these AC transport aircraft generators, the magnetic fields are electromagnetic fields, so they can be turned on and off. If you turn off the field windings, if you turn off the electromagnet, it stops producing electricity. So when you turn these on, it tells that GCU, the generator control unit, tied to each generator right here, one on number 1 and one on number 2. It tells that generator control unit to send a small amount of current through the field coils in the generator, and that causes it to produce electricity. Okay. The APU has a similar switch. Again, you turn this on, it energizes the field coils, and now the APU generator is going to run. Okay. And then these generator contactors, you can see the things that move normally are going to be automatic. So if the APU is running, they'll configure to get power from the APU, come down. Let's go back a little bit. If just the APU is running, you saw in our early example, power is going to come from the APU onto this line right here. It'll go up, and these switches will go this way. And this switch will be this direction. They'll both be down, supplying power to each of our buses. Okay. But as soon as we turn on the generator, that's if the APU generator is running, or it could be this is down to the external power source as well. We can have external power coming in and going this way as well. Either one, APU generator or external. It's going to be one or the other. The switch right here will go one way or the other. But as soon as we turn on these engine switches here, now power is going to flow. Power is going to flow from our generator. This tie contactor is going to be in this up position, and it'll allow power to come down to AC bus 1. As we turn on generator 2, it'll do the same thing. However, if we need to make a change, if we need to manually override it, or if there's something that didn't operate correctly, these lights down here will work. So these are a fail off. If the generator fails, the light comes on, and we can manually hit the off button to pop this over to the other side to either be able to get power, for AC bus 1 to get power from generator 2, or for AC bus 1 to get power via the APU by pressing this button. Right side has the same thing. It controls these two switches. Down in here, we have our essential bus, and same thing. Our essential bus right here is designed, it can get power from 3 places, and that's what this switch does. Is normally it's run from bus 1. This is the normal position here. Okay. But if we have a problem, it can also get power from bus 2. This switch here in the middle switches to the right. This one stays where it's at, and now power can go from bus 2, and it can come down through here into the essential bus. Okay, that's the alternate, that's that transfer switch. There's a third one, the emergency power contactor down here, the one that's covered by the yellow circle. That one moves the essential bus over to the air-driven generator. And that switch is controlled, I don't have it on this panel, there's a little emergency power panel on the center pedestal of this aircraft that switches this emergency power contactor over. If it doesn't automatically, under normal circumstances, normal emergency circumstances, if the ram air turbine has to deploy because we've lost all other power, that contactor is supposed to flip over to get essential power from the ADG bus. But if that doesn't happen, there is a button down on the center pedestal that allows the crew to override that. The power control on our parallel bus system is this panel that I discussed earlier. And so here is, again, it's a layout, a schematic layout. So here's that bus tie, that sync bus. Sync bus or tie bus are kind of interchangeable names, so you can see that here. And we have our AC buses shown, right? We've got the little rectangles that show the buses, I mentioned this. And then the bus tie breaker are the switches you use to power them. Now the generator breaker, the generator has two right here. So the first one is the generator itself. We turn this on, and that's the field. That's what I was talking about. You need to have an electromagnetic field to generate the magnetism that the generator uses to generate electricity. So once the engines are running, you turn this field switch on, and that'll give you power. The generator will produce electricity. And then once it's producing electricity, you have to get the frequency in phase. And here is that frequency knob I was talking about. The lights to do this are actually just right here. Here's one of the blinker lights. There's another one about right here. Those are the syncing lights. This is this panel that you kind of just see is the sync panel. And so once you get this thing running, you have the field energized. The generator's putting out electricity, but you don't close the generator breaker right away. You have to parallel the generator to the sync bus up here. You use this knob to do that. And then once you've paralleled it, once you've gotten that frequency in phase, that AC power in phase with the sync bus, then we can close, the generator breaker here and bring power up to the AC bus itself. Okay, and this works the same for bus 1, generator 1, bus 1, generator 2, bus 2, and generator 3, bus 3. Okay. So I'm going to stop there